All right. Good morning. Someone asked me about office hours. Is the person still here? The person that asked me about office hours? All right. So, office hours is on the landing page and is Monday at 10. Very often on a Wednesday I'm available also. Sometimes we have faculty meeting, or this morning, for example, there was a talk. But this is another good time. And otherwise, send me an email. I'm always here. It's just a matter to make sure that I am in my office when you want to come. All right. When did you send the email?
A couple of weeks ago. I wasn't going to show up to your office meeting on Monday. It's not on the textbooks I sent you.
Oh, yes. Thank you. Somewhere.
Yeah.
Yes. Thank you for sending the textbook.
Yeah,
Yes.
Of course. I was just trying to figure out a time to stop by because I was.
You can try anytime.
Okay. All right.
And thank you for sending the textbook. By the way, since we are here in the textbooks, open books, there has been a few additions, and then there are a bunch of very interesting textbooks which I'm not sure they are open, meaning there is a copyright or not. So I'm not putting them there just to avoid any problem. I'm sorry? And so here I put the one that I know that they are open because it's written clearly there. Typically when people put the stuff on the internet, it's open. So my slides, for example, everyone can go there and read them. That's perfectly fine. And so if you find open books that you think that are interesting, I'd be delighted to add them to the library. And I think sometimes reading the same subject in different textbooks may be very helpful. All right. So thanks again. Any comment, question about this stuff before we talk about the material? All right. So I would like to briefly review the key concepts that we discussed last time, the difficult one. So, what was the key concept? At least the name you should remember by now. Countable, right? And associated, countable and infinite, which we say countably infinite. And then there is something that is not countable. So how do we say? Not countable or uncountable. All right, when do we say that a set is countable? Yes?
If there's a bijection with the set on the natural numbers.
Yes? If there is an injection between the set and the natural number. And so, is the set of the students in this classroom countable? Yes. How do we show it? Well, I have to make an injection, right? So, I inject her in 0, E in 1, her in 2, 3, 4, 5, 6, 7, 8, 9, and I go over all the students of the class. I shouldn't skip any, I shouldn't count any twice. And this is really what we do when we count, right? We start counting from 0. It makes you very upset. You can start from 1. It's just a matter of shifting things. So it's still an injection. Alright? Countable. Injection in the natural number. The other one, countably infinite. A bijection. And then, since we have this concept, there must be things that are not countable. What are these things? A set which supposedly is very, very large. Right? There are so many that we cannot make an injection in the natural number.
So you said
A bijection, yes, this is the definition.
So my question is bijection between what?
A bijection between your set and the natural number.
And your set would have to be
Well, if you have a bijection, of course it's equal, right? Yes?
So,
Oh, you move a place.
understanding the accountability, so injection doesn't have to naturally exist. You can create one, right? So, like for example, with us, we don't naturally correspond to the natural numbers, but you can just assign us a number and count us.
Yes.
And like for example, with countably infinite, you said like the even natural numbers, you can create a bijection
Yes.
by dividing it by 2.
Yes. And so, sometimes to prove that something is countable needs a little bit of creativity. But there is a very pedestrian way to do this. If you can write all the elements one after another, no one twice, no one skip. Now, all of a sudden you have the bijection, right? The first one with 0, the second with 1, the third with 2. So really, saying that something is countable means that you can write them one after another. Of course, writing one after another mathematically is not precise enough. So we talk about the bijection. But conceptually it's the same thing. Alright? So after this we saw a bunch of examples of countable things. Some more surprising than others. What is the most countable thing of all? The natural numbers, where the bijection is you send x to x. What are things that may be a little bit surprising? Yes?
Rational numbers?
The rational numbers. Why? Because the feeling we have is that they are so many more than the natural numbers, right? If you take two rational numbers, you always find one in between, different from the two. So since that there are so many much more, because natural number, if you take two consecutive, there is nothing there. And there you can put one in the middle, and then one in the middle of the 2 half, and one in the middle of the 4 fourth. And yet, this is countable. How do we show that this is countable? With the grid, very good. This is called Cantor enumeration, which basically you make all the pairs. All the pairs are more than the rational, right? Because some pairs are not rational, the one that has 0 at the denominator. And so this is a countably infinite. We also saw things that looks like there are fewer elements than the natural numbers, and we still make the. Can you tell me a set that looks smaller than the natural number and still is countably infinite? The even numbers. Our intuition is that they are only half of the natural number. Yet you have the bijection. Alright? And so then we look at something which is not countable. And you remember what is this set? Yes?
The set of infinite strings? Or
Yes, the set of infinite strings. Infinite is important. Strings over what?
binary ones and zeros?
Right, they're just two symbols, 0 and 1, or true and false, or whatever, just two symbols, or red and blue. How did we show this one? Well, we really showed that we cannot write them in a line, and that reinforces what I said a second ago, that in order to be countable, it's just enough to write them in a line. We showed that you cannot write all these things one after another. No matter how you write them, you forget one. And of course, once you find the one you forget and you throw it in, you are going to find out that you forget another one. And no matter how many times you do this, always one is left out. And so there is that beautiful proof of the diagonal, where you take the diagonal elements of this allegedly enumeration of all the strings, and you flip 0 with 1 and 1 with 0, and of course this one wasn't there to begin with. Alright? So from this one, you show that some other set is not countable. One is the power set of the natural, because each subset of the natural, you can write it as a string of 0 and 1. 0 if the element is not there, and 1 if the element is there. And so the set of all the subsets of the natural number is in a bijection with the strings of 0 and 1, even strings of 0 and 1. So if one is not countable, the other one is not countable. You make the same proof for all the languages over some alphabet. One language is countable because you can write all the strings one after another. For example, in alphabetical order. But the set of all the languages is not there because, again, every language you change it into an infinite string of 0 and 1, and so we go back to an uncountable set. So what are the consequences of this? One is that if you want to know the decimal representation of a real number, for some real number we can, but for the majority of real number we can't. So if you have a number like pi or the square root of 2 that we can define, yes, you can do it, and there are programs, I think for pi they counted a billion or 5 billion digits. But of course there are many more real numbers than programs, and so we don't have enough programs for all of them. And this shows that there are things that we cannot compute. Why it is so? I don't know. If you believe in God, it's because God didn't want you to do it. And it's hard to find better explanation than this. It's just how math or computing is about. And it's a very surprising result, because we can define the things very well, and yet we cannot write an algorithm for computing. All right, enough of this. Any question about this? Don't be shy. All right. So now we move on this, and I think that today we comfortably will finish the section on counting, which creates a problem. Because once we, oops, you are not seeing anything, so you are not seeing the problem. Because once we finish the section on counting, you have all the information for homework number 5. And because we skipped the homeworks at the beginning, now we are running into the problem that we have to do 2 in the same week to catch up. So how do you want to solve this? Yes?
Since we usually get a week between homeworks, just say it's due on Wednesday.
Oh, do on Wednesday rather than on Monday.
Yeah, week 4 on Monday.
Hey, it's not a bad idea. I didn't think about that because I wasn't smart enough. Or because I didn't think that I had to do it, probably, right? All right, so, any other idea? Yes?
Is there a window on the midterm week that we could fold it into?
Yes, but then you fall behind in the sense that you take the midterm on material on which you didn't do the homework. So this is not an ideal situation. I think homework should be in sync with the lecture. So after the lecture, you test whether you learn or not. I'm open to suggestion and to run 1 week behind, but I don't think it's a good idea. Anything else? Yes?
I think since, well, PSU doesn't celebrate President's Day, we will probably have some absences on Monday because of President's Day. It's not ideal to have 2 next week, so I would suggest maybe the following Monday we have 2.
All right. How many people agree with that? How many people disagree with that? Well, I'm sorry. We spoke about the one size fits all, right?
Right?
We have to have it in sync for grading and everything else. So, unless I hear otherwise, we have number 4 on the 20th and number 5 on the 22nd. Any objection? All right. I'll write it there for the people that are not here today. So counting, this part of counting that we are going to do now is called combinatory. And this is the situation. We have, yes? No, the reason is that once you see how to make an extra, you can make it very easily as well, right? What I do is that the numbers that are there, I pick one more or one less, and you create a new problem. All right. So I have a set where I have n objects, and I want to create a subset or sequences where I pick some of these objects. And so the easier case is a permutation where you have n objects, and in this example my n objects are 4, and these are the digits 5, 6, 7, and 8. And here I want to pick all the possible way in which I arrange 2 of these digits. I intended different, not the same digit twice. And I wrote it there. I hope I didn't forget anything. If I show you how I computed that one, you'll probably get the sense that I was right. So, my set is 5, 6, 7, and 8. And I want all the sequences where I pick 2 of these elements. So I say, look, the first one I can pick either 5 or 6 or 7 or 8. Are you with me? There are no other options. So now that I pick the 5, what can I pick for the second? Either 6, 7 or 8, right? And here, what can I pick for the second? 5, 7 or 8. No 6 because 6 had been picked already, right? And so the same one for 7 and for 8. So in how many ways can I do this? 12. And I wrote all 12 here, if I didn't forget anything. And so this is an example. In the general case, what do? I represented this as P and K, where n is the number of objects I get, and k is how many I pick. K can go from none, which is not very interesting, 1, which is not particularly interesting, or all n. and P stands for permutation. And how many do I get? So the first one I can pick in n possible ways, right? Like I just did in the example. The second, because now 1 is gone, I only have n minus 1 possibilities. And then the third, I have n minus 2, because I spend the 2, 1 for the first, 1 for the second. And I go until the kth. And that one is n minus k plus 1. Why do I have that plus 1? Because I start with n. I start with n, right? And so, this is the number. Should we apply this to the previous problem to see whether it works? What is n in the previous example? 4. What is k in the previous example? 2. So I go from 4 to what? N minus 2 plus 1, which is 3. And so I only have a 4 and 3, 12, which is exactly what I got there. Yeah? There was a question there.
So when you're writing, so the permutation of 2 digits from the set,
Yes.
are the possible permutations technically considered sets with 2 elements, or are they?
Any number. Now we are going to do something else. Any number.
I'm talking about the product of the permutations, like 5, 6, 5, 7, 5, 8. Is that how do we interpret those?
So this is a sequence of 2 elements taken from there,
Okay.
without repetition. So you cannot put there 5, 5 or 6, 6. Once you take it, it's gone. You see there that I have n times n minus 1, and then I have those dot dot dots, which mathematically are never an ideal situation. So here I want a closed form. How do I get a closed form? I cheat shamelessly. I say, look, I invented these things, bang, factorial. And this means n times n minus 1, n minus 2, up to n. Now, the dots are gone. I have to invent a new operation to do this. I make the convention that 0 factorial is 1. Because if you don't take any element, how many sequences you have? Just 1. So, works nicely. Works also in this case. The problem is that n factorial wants to go from n down to 1. But the permutation goes from n down to n minus k plus 1. So how do I fix that? And I have this formula, which is very easy to understand, right? So here, first let's see what is in this case. Yes, thank you. Let's see what is in this case P of 4, 2. We said that this is 4 times dot 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 3. Right? Really, there is nothing there. I don't want the dot. So what do? Here I say, let me do this 2 factorial, multiply, and here let me divide for 2 factorial. Right? If I multiply and divide by 2 factorial, I haven't changed anything. And so now, when I have 4 times 3 times 2 factorial, what do I have? 4 factorial. And so this one becomes what? 4 factorial divided 2 factorial. There are no dots. And so I got what I wanted. I didn't want dots. I don't have any dots. Enjoy. So there are some special cases. I already mentioned 0 and 1. what is the Pn1? The formula will say n. Why? Because you go from n to n minus 1 plus 1, which is n. So you only have n. Does it make sense? Yes, you are picking only one element, you either pick the first or the second or the third up to the nth. So Pn1 is n, which fit the formula. The other example is when you pick a Pnn, which means that you pick all the elements, right? So k is n, so you go from n to n minus n plus 1, which is 1, and you have n factorial. You with me? Pn1, yes, let's see what is Pn1. Let's see what is the meaning of a Pn1. Let me write it here. Pn1, and then let's see how it fits with the formula. First, what is the meaning of Pn1? Alright, so I have these n elements in my set, and I consider the sequence where I have only one element. How many sequences there are? N. One when I pick the first, another one when I pick the second, up to the n when I pick the last. Now, if I apply the formula here, what do I have? This, according to the formula, is n minus 1 dot 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 n minus k plus 1 divided k plus 1. What is k plus 1? Is 1 factorial, which is 1, right? What is this value? N minus 1 plus 1. So this is just n. This entire thing here is n. So is n divided by 1. And so Pn1 is n, exactly as I expect. Yeah? Good. So this one is relatively easy to understand. Everything else, we bring it back to this one. Every other computation that we do this morning, we bring it back to this one. So it should be relatively easy. Let me show you a little bit where I'm going. I have my set of n elements. Basically, I can have two parameters when I pick an element from the set and I arrange them. One is whether the order in which I write them is important or not. A sequence, the order is important. A set, the order is not important. So basically, from these elements, I make either sequences or sets. Sequences, the order is important and set is not. So I have one dimension here, which I could call order. The other dimension is whether I allow repetitions or not. Whether I have a set where there is the element 5 and I can put the 2 copies of 5 in whatever I'm doing, or I'm not allowed to do that. I don't want repetition. Alright? And so, this is an orthogonal coordinate. I can allow yes or no repetition. I can allow yes or no order. They are independent. And so the other one is repetitions. And what are the cases? Here I can make a table where I say yes, no, yes, no. All right? So the case of permutation, which of these 4 boxes I cover? Is the order important in what I'm doing when I do permutations? Yes. Do I allow repetitions? No. So which box is? this one here. Permutations. All right? Yes?
So, if order is important, does that not mean that no yes is different from yes no?
So here, by yes and no means order, oh, I don't know. So let me be more precise. Order. Counts or no counts? Or allowed. What does it mean allowed? Let me say counts or matters. All right?
Sorry,
This is what I meant with yes. Maybe this is more precise. Say it again?
I just misunderstood the graph, I'm sorry.
Yes. Far so good? All right, we are going to do more examples as we go along. So the next one is combinations. So here I take again k objects, but I don't distinguish the order. The order here doesn't matter. So if we look at this one that I was doing here, when I counted these, here I have, let me do it in red so you'll see it better. Here I had the sequence 5, 6, and here I had the sequence 6, 5. Yes. And I count both. I count the first one and I count the second, and the total is 12. Right? Now I say the order doesn't matter. It's not important. It doesn't count. So 5, 6 and 6, 5 is the same. Instead of considering a sequence where I have a 6 and 5, I consider a set. So the set 6 and 5 is equal to the set 5 and 6. Because in set the order doesn't matter. Alright? So how do we count this one? Let's consider another example and try to understand how we get there. Suppose that I have 3 elements. 1, 2, and 3. Alright, this is my set. If I consider the permutation of 3 elements from this set, how many permutations I have? This is 3 factorial, right? Which is 3 times 2 times 1, which is 6. Should we write all of them? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Typically, if you write them in order, it is easier to make sure you don't miss any. Alright? Now, if I disregard the order, I say the order doesn't matter. How many elements do I have? Alright, so what are these 3 elements?
1, 2, 3, 2, 1, 3, 3.
Well, if the order doesn't matter, they are the same. 1, 2, 3, and 2, 1, 3, the order, they only differ by the order. Right? There is only one. Should we play a little bit more? Suppose that instead of taking 3 elements from this one, I take only 2. What do I have? 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. Yeah? Yes?
That's a permutation.
This is the permutation. These are all the elements. If the order doesn't matter, how many do I have? 3. Why? Because 1 and 2 and 2, 1 is the same. 1, 3 and 3, 1 is the same. 2, 3 and 3, 2 is the same. Do you get any idea how to compute this?
So if it's n number of elements in your set equals 1, is that correct?
So here the idea is that now we know very well how to compute permutations, right? So if the order doesn't matter, how much do I overcount by counting permutation instead? Well, in that case, a twice as many. But in this case, a 6 as many.
Is it k? It's the factor of k.
You are almost there. Yes? Is k factorial? Why is k factorial?
It's all the possible.
Because all the possible way you can rearrange them, right? All the possible way you can rearrange them. So, you see the formula here, the combination. Says, look, first let's compute the permutations, right? What is the number of permutations? Number of permutations will be n factorial n minus k factorial. This is what we just learned, right? Now, if there are k elements there, what is the overcount? It's k factorial. Because these are all the possible way I can rearrange those elements. So I divide all this by k factorial, which really is the same as n factorial, and yes, sorry. Here I divided this one by k factorial, which is n factorial, n minus k factorial, k factorial. Why for the combination I have that extra k factorial? Because these are all the possible way in which I can rearrange the k elements, which are the permutation of those k elements. So should we now try to apply this one to the two examples that we just did to make sure that everything works? So here I have in this example here, I have a C 3, 3, right? So this 3, 3 is 3 factorial divided by what? 3 minus 3 factorial, which is 0 factorial, times 3 factorial. Right, this is n, this is k, this one is n minus k. And so I get 1, which is exactly what I expect. Right? Here I have a set with k elements. I compute a subset where I put all the k elements. In how many ways can I do it? Only one, just by putting all the elements, and that's it. Right? Should we try to do the other one? Here I do the k 3, 2. K 3, 2. So again, this is n and this is k. So this will be 3 factorial times what? 1 factorial divided by 2 factorial. where this one is n minus k. And so what is this one? This is 3 factorial divided by 2 factorial, which is 3 times 2 times 1, divided 2 times 1. I simplify and I get a 3, which is exactly what we found before. Right, before we said, look, the elements here are 1, 2, 1, 3, and 2, 3. As set, if I write everything precisely, I write it this way. These are the 3 elements. Yes? Yes, sorry. Yes?
So on an exam, how will we know the difference? How will we know the difference between the ordered and unordered version? Because the ordered version will always be referred to as
So this can be phrased in several ways. But if I say permutation and combination, of course, you know exactly, right? If I say, in how many ways can you arrange? Is the order matters? If you change the order, you change the arrangement or not? Yes, of course, right? When we talk about combination, we also say how many subsets there are. If you look at this one here, I ask you, how many subsets of 2 elements there are in this set? Subset doesn't consider the order, right? And so the question should be clear enough because I use either the word permutation or combination, or say arrangement, or I say subset. So if we go back to that matrix that I did before, where are the combination? Here. So we go from one to the other, right? And so now we consider similar things where we allow repetitions. So in the object that we compute, we can put the same element more than once. However, there is something very important to understand here. That the rules of the game are not the same for the 2 squares that we are going to fill. In the right one, you can do repetition in any way you want, totally unrestricted. But in the left one, we will put some restrictions on the repetition. Why? Because if we don't put the restrictions, we don't really know how to compute. Or it's getting too difficult for this class. Alright? So I think that it would be good now, before we face those two, we take a break, even if it is a little bit early, so then we don't have to break when we are in the middle of the more complicated one.